1.5, continuity continued and the IVT. So just as a refresher, we have a continuous function on the left and a non-continuous function on the right. And for a function to be continuous at a point, the left-hand limit has to equal the right-hand limit, and it has to equal the function value. So we're just going to review that a little bit and combine that with our idea of limits at infinity. So we're determining where or what values a function is continuous at, and then we're looking at end behavior. So the places it wouldn't be continuous were the individual graphs were discontinuous, or at any of the parts where we're jumping. So we look at this part first, 1 over the quantity x plus 3. So immediately, we should know there's a vertical asymptote at x equals -3, so it's discontinuous there. Okay, so we'll keep that in mind. And now we just need to check all the different jumping points. So the limit is x approaches -2 from the left side. That's the 1 over x plus 3. We put in -2, we get 1. Okay, the limit as x approaches -2 from the right side. This time we're looking at 2x plus 5. We get 1. So that's good. It's continuous at -2. We're good there. We're also going to check 2 and 4. Clear out. Alright, so the limit as x approaches 2 from the left side. Limit as x approaches 2 from the right side. We get bored. So discontinuous there. Just keep it in your left side. You should keep it on the page, but for the sake of how my computer's working, I'm not. Okay, limit as x approaches 4 from the left. That would be 16. Limit as x approaches 4 from the right. So it appears it's continuous. However, where would you plug in 4 to get the function value? You can. It doesn't equal 4 anywhere, so it's discontinuous there. So we needed to determine the values at which the function f of x is continuous. So we can write that out. F of x is continuous. Reals on a real number except x equals -3, -2, 4. So now we're going to do the end behavior limit as x approaches -infinity. So we're looking at -infinity. So that graph is x gets really, really big. This is approaching 0. Limit is x approaches infinity. Okay. It's going to grow slowly, but it's still going to grow and grow and grow. So it's going to be infinity, or you could write does not exist. So now we talked about continuity at a point. So now we're basically expanding that to not just a point. Now it's continuity on an interval. It's continuous on an interval if it's continuous at every point. It seems to make sense. And now, written a little more specifically, a little more mathematically correct, it's continuous on an open interval if it's continuous at every point inside the interval. It is continuous on a closed interval if it's continuous on the open interval and the endpoint limit as x approaches that endpoint equals the endpoint. All right, we'll see an example. So determine the largest interval between 0 and 3 closed, which the function is continuous. So we can't. because we don't have any let's do it from memory. That equals 0. F of 0 equals 0. So that means that it is continuous at 0 all the way up until, let's see, it looks like 1. Okay, so we have a limit as x approaches 1 from the left. That equals 2. And then f of 1 is 3. So it's not continuous at that interval. At that endpoint. Because the limit, one-sided limit does not match the function value. So this is one interval. Another interval, it looks like it would be using the same reasoning from 1 to 2, including 2. The limit would match the function value. And also from 2 to 3, including 3. So any of those values would be continuous on those intervals. Example 3, we have a really nice graph there. Graphus interruptus. And so we're going to be using this graph to answer a few questions. On the interval, list the largest intervals for which it's continuous. So I'm going to just start left to right, because it's easier for me. So it looks like negative infinity, it would be all the way up until negative, what is that, 2? I can't include 2 because f of negative 2, sorry, is 2. And that doesn't work here. Let's see, the next one would be negative 2, not including it. Again, we'll start here, going all the way to 2. Now I can't include 2 again because the limit as x approaches 2 from the left does not equal f of 2. So let's see, I can also say all of these are really small intervals. I could write them just to have them there. 2 to 5, and then let's see, that would be 5 to 6. That's not a very big interval though. Largest intervals. So I'll just jump to the end. It looks like 11 all the way to infinity. And remember, we never include infinity because it's not actually a number. It's approaching a number. Next question, find the largest value of b such as the function is continuous on 5b but not in 5b plus 1. So let's assume b is an integer. So we want it to be from 5 to something, closed interval, but not in 5 and then b plus 1. So let's see, is it continuous at 6? Yeah, it looks like it is. But is it continuous to 5, 7? Alright, so let's see what that is. So here is 6. It looks like that is true. So if b is an integer, this would work if b equals 6. But it would not work if we replace it with 6. 7, but not in 5. Because 6 is here, and we have 7, 8, 9. It's just a little easier to see. And then if b is not an integer, it wasn't specified. Not an integer. Then it would be any of the values. We could say all b in between 5 and 6. You're going to see this kind of problem a lot. All right, now we're looking from some number to 10, and we're giving the largest interval. let's see. So looks like at 8 we have a hole, so we're not going to get too far. So I'm going to say 8 to 10. Okay, and this is what other values could be. It could also be 8.5. It could be 8.2. It could be 9. So to say the other values, we would say anything between 8 and 10. Find the smallest value k such that the function is continuous from that number to infinity. And we already kind of mentioned that in the first problem. That would be 11 to infinity. So that equals 11. It couldn't be 10 because we have a hole there. And it would not be 11 because this were the case in the next example. It cannot work because the limit as x approaches 11 from the right doesn't match f of 11 because there is no f of 11. So this time, if it's an integer, k has to be equal to 12, or more specifically, k just has to be greater than 11. So that should do it for this section, this video anyway.